Hello, my name is Milan and I'd like to present you the Hitchhiker's Guide to Prior Shift Adaptation. In the framework of empirical risk minimization, we typically assume the training data to come from the same distribution as the expected test data. However, in many classification tasks, the class prior probabilities on the test set differ from the training set priors, while the class conditional distribution remains unchanged. Let us use the subscript T to denote the training set distribution and subscript E to denote the evaluation or test set distribution. Let's have a probabilistic classifier estimating posterior probabilities. For example, a softmax classifier trained by cross-entropy minimization. When the class prior probabilities change, we can use the Bayesian theorem to derive a simple formula for adapting the classifier's predictions to the new priors. The new predictions are proportional to the original predictions multiplied by the ratio of the new and the old priors. The new priors, however, are often unknown and we have to estimate them. An existing procedure for estimating new priors uses a confusion matrix containing the probabilities of classifier's decision given the true class. Notice that a confusion matrix in this posterior form does not change with prior shift. Now we have the relation between the class priors and the probability of classifier's decision. In the standard procedure, the new priors are then commonly estimated using this formula, estimating the probability of decisions by the relative number of classifier's decisions on a set of data from the new evaluation distribution. However, such estimation sometimes results in negative values. Previous works have noticed that, but the authors assumed it is a numerical issue. We show that the confusion matrix defines a convex set of feasible values for the probability PD of classifier's decision within the probabilistic simplex. The problem with negative values in the estimated priors thus comes from inconsistent estimates of the confusion matrix and the probability of classifier's decisions. To overcome this issue of the existing method, we propose a maximum likelihood estimation approach based on the confusion matrix. Assuming the independence of classifier's decision on the test set E, the likelihood of classifier's decisions Q follows the multinomial distribution. We maximize the log likelihood with condition on solutions on the probabilistic simplex by optimization with projected gradient ascent. The proposed method can be simply extended into a maximum a posteriori estimation by adding log concave hyperprior. Specifically, we use the symmetric Dirichlet function as hyperprior as it was used in the related work. Our experiments with prior shift on several computer vision datasets show that the proposed methods bring a consistent improvement against the standard confusion matrix-based prior shift estimation. The proposed maximum likelihood methods are denoted with the superscript L for likelihood. CM denotes the confusion matrix computed from the classifier's decisions, and SCM denotes a soft confusion matrix computed from the classifier's softmax predictions. The proposed methods achieve competitive results against the state-of-the-art algorithms for prior shift estimation, both with and without classifier calibration. Experimental analysis of the existing and proposed methods for prior shift adaptation suggests the following best practice. Adaptation of the original classifier performed better than retraining with sampling matching the estimated shift. The proposed method handles inconsistent estimates of the probability of decision and the confusion matrix, and it consistently improves the results both using the confusion matrix and the soft confusion matrix. The proposed prior shift estimation methods achieve state-of-the-art results. The EM algorithm works better in cases with a low number of samples. The proposed MAP approach performs better than the previous methods. It is better to estimate test set priors than to estimate the prior ratio explicitly. Please visit our poster to learn more about our methods and experimental results.